Hey there, Gregory Carlson here with the Calculus Building, and we have a few more examples to go. And this one is going to be a little rough. You know that when we take the derivative of a fraction, we use the quotient rule and we get a big old fraction. And then we're going to need to take the derivative of that bigger fraction. So let's do it. First, let's find y prime. I might write a little small on this one. So it's low times the derivative of the high minus the high times the derivative of the low. So please make sure you got all of that. That's the low times the derivative of the high minus the high times the derivative of the low, all over low squared. Okay, so there we go. And let's actually go ahead and clean this up a little bit, especially the numerator. So the numerator, let's see, this is going to be 6x plus 9 up here, right? 6x plus 9. And this is going to be, if we multiply both of these, it's going to be negative 6x minus 2. Oh, that's actually going to work out nicely. So that means we only have the number 7 on the numerator and 2x plus 3 squared in the denominator. So that's y prime, which again is shorthand for dy dx. So I have 7 over 2x plus 3. Let me just make sure that was 6x plus 9. This would be minus 6x. Oh, that should have been plus 2. That should have been plus 2. So that should have been 11. Sorry about that. Okay, so we have, let me rewrite that. So we have y prime equals 11 over 2x plus 3 to the second power. And so now let's find y prime prime. So do the quotient rule. You know, I'm not gonna do the quotient rule here. I'm gonna show you better practice. We're gonna move this upstairs. So this is y prime is equal to 11 times 2x plus 3 to the negative 2 power. Is that okay? And now let's just do the power rule with the chain rule. So y prime prime, that's going to be negative 22 times 2x plus 3. Take off 1 power, so that's to the negative 3. And then times the derivative of the inside would be times 2. So the final answer is y prime prime equals negative 44 times 2x plus 3 to the negative 3. And if you want, you can move that down to the denominator. Cool beans. So if we had extra terms up here, you just would have needed to do the quotient rule. And be careful, because if you'd done the quotient rule with this, you would have needed to do the chain rule as part of the quotient rule in the low-d high, high-d low. And we've already seen examples like that, so I'm just going to skip it. This next one, for g of x is equal to the following function, find g6x. So that means find the sixth derivative of this. Now remember, a few videos ago when I first introduced higher order derivatives, since I don't have any x's in the denominator, if I take the derivative enough times, the derivative should always be 0. Okay, so will it be enough? I think this is going to be enough times, because I think this is going to gobble it all up. And so let's just take the derivative of this just to be safe. So the first derivative of that, g prime, would equal, the 4 comes down and cancels with that 4. So that would just be x to the third. G prime prime would equal 3x squared. G prime 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 would equal 6x. G to the 4, meaning the fourth derivative, would equal 6. And we see that the fifth derivative would equal 0. So this is equal to 0. And there's a few other functions that can survive derivatives, and we'll look at those a little bit later on in calculus. And so just remember that rule that if this number is equal to the highest power, it's going to be some factorial potentially times if there's any number out in front. But if this number is higher than your biggest power, once you just keep taking the derivative, as long as there's no x's in the denominator or something else going on that's weird, you're going to get 0. So let's wrap up higher order derivatives with an application problem. When an object is dropped on a planet, the distance it falls is in t seconds, assuming we're ignoring air resistance. We have this equation. So here's our position function. So suppose that a medic's reflex hammer is dropped from a hovering helicopter. Find how far the hammer falls in 4 seconds, how fast the hammer is traveling 4 seconds after being dropped, and the hammer's acceleration after it has been falling for 4 seconds. Okay, so I haven't really given us enough room for this, but it should be okay, because do you agree with me that f prime of t, that's the first derivative? That's going to be 28t, and the third derivative, or the second derivative, is just going to be 28. So look how easy it is to calculate the gravity on other planets. I mean, granted, in real life it would be a little bit trickier, but not that much trickier. The calculus still applies. So this is the amount of distance it's traveled since he dropped it. This is the speed that it's going, t seconds after it's been dropped. And this is the acceleration. So we can see that the acceleration, like gravity, is a constant number. So that's good to know. So how far has it gone after 4 seconds? Well, we would just plug in s of 4. So 4 times 4 is 16. And 16 times 14 is equal to 224. So it's fallen 224 feet since he dropped it 4 seconds ago. If we plug in 4 into the derivative function, that means that that's how fast it's going after 4 seconds. Again, these are pretty easy calculations. So the units on this should be feet per second, because that's a velocity. So after 4 seconds, it's traveling 112 feet per second, and you can see that every second that passes, it's going to be getting faster and faster and faster until it hits the ground. And we see that s prime prime of 4, there's no t to plug 4 into, so that's just 28. So its acceleration is constant, and that would be feet per second per second. So it's accelerating 28 feet per second a second. Okay, so the velocity is what's changing here, and so that's why the feet per second is changing. Or you can think of it as 28 feet per second squared. But when I was first learning this, I got so confused by the seconds being squared. I got so confused by that. That's why I always like to say 28 feet per second, because that to me makes more sense. Last application problem. A company determines that monthly sales in thousands of dollars after T months of marketing a product is given by this function. So this function is the total monthly sales every month, where T is in months. So they want us to find the first and second derivative, so let's do that really quick. I'm just going to do this real quick. 9t squared minus 2t plus 10 is the first derivative. Second derivative is 18t minus 2. So hopefully you're okay with those two derivatives. So find s prime of 2 means just plug 2 into this. So s prime of 2, that would be the rate at which sales are increasing. And so that would be 9 times 2 squared would be 9 times 4 is 36, minus 2 times 2, which is 4, plus 10. So that would be 32 plus 10. So we could see that 42 So we see that this is really good news for our business, where our sales are increasing $42,000 a month. So we're selling more and more and more, and we're going to be selling more and more and more. It's like a viral explosion of people buying our products. So if we interpret the second derivative, plug 2 into this, it would be 36, 18 times 2 minus 2. So we see that that would be 34. So our sale acceleration is itself accelerating, okay? So our sale acceleration, yes, our sales are doing better and better and better each month, but that is in itself accelerating. And so in other words, if we were to find the rate of sales at 3, we can actually find it fairly easily, because it would be 42 plus about 34. I mean, that won't maybe be exactly right, but In fact, let's see what it would be. Let's see, s of prime of 3, if I plug 3 in here, would be 3 times 3 is 9, 9 times 9 is 81, minus 6 plus 10 is equal to, that's the same thing as plus 4, so that's 85. And if we add these two together, we see that these two added together is 76. So why has it not increased all the way to 85? Why does it seem like if we add this acceleration, it seems a little bit lower? The reason is because this was the second derivative at 2. So that's going to be a little bit smaller than what the second derivative was at 3. So that's going to underestimate this a little bit, because if we had found the second derivative at 2.9, then it might have been, or maybe 2.5, then it might have been a better approximation. So, because just remember, the second derivative is that instant in time at 2 months that our sales rate is increasing at 34,000 a month per month. I really hope all of this is making sense to you. I hope these videos are helpful. If this is, please make sure you like and subscribe and share it with your friends. If you have questions, please leave them in the comments. My name is Gregory Carlson, and I'll see you in the next video. I hope you have a wonderful day.